we saw Markov chain. We saw that it is a special kind of stochastic process, slightly more general than random variables being independent. More specifically, a sequence of random variables were called a stochastic process. We saw that a very specific case of it was Markov chain, specified by this particular property, that if I look at the value of the k plus 1th random variable conditioned on the variables before, we can say that it only depends on the value of the kth random variable. So for a general stochastic process, this thing will depend on all the random variables, this expression. But for a Markov property, it only depends on the kth random variable. You can think of it k as the present. What happened in the future depends on the present random variable. It encodes whatever has happened in the past. So this was the Markov property, and we also assumed that the Markov chain is going to be homogeneous. That means this transition probability does not depend on time. So where xk plus 1 and xk are some elements of the state space. Remember, for a stochastic process, the state space does not change. And then this becomes a homogeneous Markov chain. And we said that we will be only looking at homogeneous Markov chains. It turned out that a homogeneous Markov chain can be specified simply by two things: initial distribution and the transition matrix. The initial distribution was the probability of x0 being in different set I for all I element of S, and transition matrix was this set of probabilities. So probability x1 is equal to j given x0 is equal to I, and this we denoted by a matrix Tij. This was called a transition matrix. There is an easier way to represent this as a graph. So if I just make my state space as vertices of a graph, I can connect them with transition probability. Let's say my initial distribution, let's call it the vector mu. This is a vector with cardinality of s many constraints. So it tells you the probability at every point in the state space. This is mu1, this is mu2, mu3, this is the initial probability. And then there can be transition probabilities which will satisfy something. So let's say from 1, I go to 2 with probability half and go to 4 with probability half. So similarly, I can define this. So from 3 to 2, this will become the transition matrix probability T32. This will become T23 and so on. So this is how I can represent a Markov chain. So my initial distribution, I will just define it as mu0. This is time step 0. And then I want to see how a Markov chain evolves. That means what is the probability distribution after 1 time step, after 2 time steps, after 3 time steps. This is what we are interested in. And we will see that a Markov chain has a lot of structure. We can actually figure out what happens in the long run. We will see an application also in the next. Let's take an example. So if my transition matrix was this is a very simple Markov chain. It has 2 states. Call them A and B. This does not specify the initial distribution. Let's say my mu is half and half. So I have half probability to be here, half probability to be here. And then with probability 1 from A to B, I move. And then from B to A, probability 1. So this is the graph which will represent this transition matrix and this initial probability. Let's define mu t to be the state at time t. Mu t I will be the probability of being in state I at time t. So let's start with the most simple case. Can we figure out what mu1 is? Remember, we are given mu0 and we are given the transition probability, the transition matrix. It will be easier if I just represent my transition matrix with letter M so that there is no confusion with the transpose. For now, this is our transition matrix. I am just changing the name for the ease of notation. What is my mu1? From the picture, it's kind of clear that I have to go to some state. Let's say I would have gone from some other state space, correct? If I want to say mu1I, this is the probability that I start in some other state J and reach I in the next step. So this is the probability that I was in J, then moved to I, and I have to multiply with the probability that I started with state. And you notice that both of these quantities I know in terms of mu0 and m. So this becomes summation over j element of S mji mu0. And if you look at it keenly, you will see that if I look at it for all possible states I, this is actually giving me a vector equation, which is mu1 is mu0 times. How about mu2? I would say that again, there has to be some state we are at state for the time step 1. Probability x2 is equal to j, given x0 is equal to I, it should depend on some intermediate state u element of S. It becomes probability x1 equal to mu given x0 equal to I multiplied by probability x2 equal to j given x1 is equal to u. And again, you can see it that this is basically multiplying as a matrix. I will let you stare at it for a while and you will realize that there is a very simple way to write the state after t time steps. So we saw that mu1 transpose was mu0 transpose multiplied by n. Then if we do it for 2 time steps, it becomes m square. And in the assignment, you will prove that after n time steps, the state can just be written as this multiplication. And this formally proves what we have been saying before, that my state in future is completely determined by just the initial distribution and transition matrix. So now we have a very nice way to say what happens in a Markov chain, how the state evolves. But we have been talking about a strong structural property. Let me just talk about it. What is the strong structural property? It will be very surprising if I say that the behavior of the Markov chain does not depend on how you start. Seems very weird to you, I'm sure. I will say that it actually don't even depend on mu. Long time behavior of the Markov chain only depends on the transition matrix. This might seem surprising, and this is not entirely true. But let's see when is it true. So again, what I'm going to say is that you remember that a Markov chain has these transition probabilities and then some initial state. And if I evolve it for a long time, so I'm looking at the state mu n as n tends to infinity. Claim is final state does not depend upon. This is not going to be complete. I have to say under some restrictions, and these restrictions are specified by something called a regular mark. The question might be, do we need some restrictions?